meeting is being recorded.
Welcome to today's masterclass. My name is Jose Rivera. I am the CEO of CSIA, and I will be your host today. On the off chance that you don't know CSIA, we are a global non-profit trade association with over 500 member companies in 35 countries. For system integrator members, the CSIA Best Practices Manual and CSIA certification are some of the more popular member benefits. You will also enjoy a variety of others, including professional development, learning from your peers, and access to professional service experts, including insurance, financial, and legal, who understand the system integrator's unique business needs. For partner members, CSIA offers an ecosystem to grow your system integration program, understand your customers' pain points, monitor industry trends, and share your thought leadership. With thousands of qualified integrators and suppliers, the CSIA Industrial Automation Exchange helps system integrators, industry suppliers, and manufacturers connect and do business. For SIs and partners, it provides a platform to support your content and search engine optimization marketing efforts, position yourself as a thought leader, and nurture prospects during their complicated buyer's journey. In case you aren't a current member or haven't renewed your membership yet, now is a great time to join and renew. Membership provides you many benefits, including a full lineup of virtual events and other resources for you and your entire team, from accounting to sales to operations, 365 days per year. Members can also take advantage of discounted registration rates for the in-person CSIA Executive Conference scheduled for June 27th to the 30th in Denver, Colorado. At this time, I would like to introduce our speaker for today's webinar, Ravi Jagasia. Before I do so, one quick reminder, we welcome your chat, put it in the chat box, but if you have questions for the presenter, please put it in the Q&A box. So Ravi, the floor is yours.
Thank you. Thank you, everybody, for joining us at this session. I appreciate your spending time here with us to know more about how to use Ethernet in hazardous area. The agenda briefly will be some history, some snippets on the history, why Ethernet-APL, why and how are we going to use Ethernet-APL, or what are the components for Ethernet-APL, including the standards, the architecture, what is a predefined port, why do we need them, cable connectors. That would typically answer a lot of your first questions of getting Ethernet-APL in your plant or as system integrators to implement Ethernet-APL at your customer's place. And then in the last, we'll also share some of the products that we are having for Ethernet-APL, which are many of them are in development stages, but we do have some ready. That's me. I've been with STAHL Group for about 14 years in various markets and various roles. Currently, as a business development and sales. For the automation portfolio, STAHL is having electrical, lighting, and automation products for the hazardous area. And I market in the, or I work in the Americas region here. I've represented STAHL at various regional bodies, the Foundation Fieldbus Middle East Marketing Committee, the PCIC, the Profibus International, and now here at the Open Process Automation Forum. My email IDs are there. You are free to reach out to me after the presentations if you have any question. The history. Ethernet was developed, designed, or invented in 1973. That was the time when Bob Metcalf actually created the first document outlining what is Ethernet, and he presented it to the Xerox management for their approval to go forward. This was to build their network inside their Palo Alto Research Center. Later on, He, as part of Xerox with Intel and digital equipment, developed the industry standard, which was operating at 10 megahertz. The one which he developed for Xerox was at 2.4. This version was then adopted by IEEE as 802.3 and released in 1983. So you can see how far we have come ahead. The development of IEEE Ethernet standard 802.3 is now with the various variants that are available, and now we can see later on how we adapted that for Ethernet-APL. Just some images here to realize what do we have or what we were working with previously when we talked about Ethernet and how compact the electronics is today. Going forward, STAHL did come up with a hazardous area solution with Ethernet, but with fiber optics. This was based on a standard IEC standards 28 published in 2006, and in 2009 we came out with the first hazardous area installable remote I/O with an Ethernet interface, of course over fiber optics. So what you see is the fiber optics here, and then the standard cable going to the switch and going into your control system. This could be installed in zone 1 div 1, and these could be installed in the zone 2 div 2. With fiber optics, multi-mode and single mode, you could travel the distance you wanted, and you could still be able to manage a remotely installed IOs from the control room. Going forward, we have the Purdue ISA 95. And in Purdue ISA 95, we do know that from the field to the control room, we use the 4 to 20 milliamps or the 4 to 20 milliamps with HART or smart transmitters. And then we definitely have the discrete signals. And from the control systems into the supervisory systems and up to the enterprise level for the management execution systems, you had Ethernet all along. This meant that there was no Ethernet into the field. And if that we wanted to do, there were many challenges. We had to take care of twisted pair cabling. We had to ensure that the solution would be loop powered because we love to work with two wire field devices. The plants are quite long, especially when you run them in the cable trays, when you run the cables in the cable tray, and that becomes a challenge. You definitely need to do maintenance. And in that case, intrinsic safety is a big help because that allows for live maintenance. You wanted to ensure that you had migration possibilities from a smaller system to a larger system. And then of course, you wanted a standardized solution which was uniform across the world and not that what you get here in the US could not be used in Europe or Asia Pacific or otherwise the other way around. So that being the requirement was the formation of Ethernet-APL. That we need to work together to evolve a solution which will be global. Some history on that as well. 1990s, we remember the field bus wars. There were 50 plus field buses available in the market, each of them fighting for the market share and trying to be the standard. Then Namur evolved in 2002, 2005 when they did the Furious study. When in 2005 they released the Furious 2, they were concluding or tried to conclude, is Fieldbus better or is remote IO better? What would be good and economical for the process industry? Conclusions were there, but going forward, not much happened. And then came Namur again with their release of NE 168 requirement that they want now an Ethernet communication system all the way to the field device level for the auto process industry. Namur, for those who are not aware, is a end user association comprising of most of the German companies in the start, but now a lot of the international companies have also been the members. They basically set up the expectations and the requirements of the end users from the process industries for vendors like us to build products and adhere to their expectation. So that's where once the demand and the expectation came up from Namur that we need Ethernet based solution, came the developments into the future. What happened was you have the A team here. You have the standards development organization from Fieldcom Group, ODVA, OPC, Profibus International, and then a lot of the vendor companies. The standards can be developed, but there's a lot of experiences these vendor companies have had over time, which could be used to see that the standards are more real than not just theory. So that's how they all got together to develop the standard. And if you are developing the standards they set and needed to set the best benchmarks, what were the benchmarks? They wanted to standardize for simplicity, for interoperability and reliability. They wanted to ensure that it is going to be minimum 10 Mbps data, able to travel a long distance, able to work with a IEEE standard, not that we need to go and develop a new Ethernet standard. Definitely it has to be two-wire, ideally with intrinsic safety built in, and then interconnections. You needed to be sure that you could be able to connect all these protocols from these standard development organization onto the standard cable at a standard rate with an intrinsic safe power supply, and then ensuring that it is hazardous area suitable. So what else was required? It was required that you needed port profiles, and we'll come more into details later, but basically that helped to have a standard architecture. You could switch between various architectures. You could do networking much more easier. And then, of course, you could standardize the cables and connectors, giving the flexibility to the end users to choose vendors without having to do a lot of rework on their They first evaluated the two-wire Ethernet, the single-pair Ethernet, already developed with IEEE standards, the 100, the 1000 base T1, going all the way down to 10 base T1L. What is 10 base T1L? As an example, the nomenclature, 10 is the Mbps speed, the 1000 Mbps was the 1000 Mbps was the 1000 base T1. T is the twisted pair, 1 is the 1000 meters, and L is the long distance. So that is how they had defined these individual labelings. And auto negotiation always required so that you have a stable communication, energy efficient, yes. But to what level? Power over data lines. We know about power over Ethernet. So you could do power devices. What was the power available? Cables, connectors, and explosion-proof concept. Definitely that was not available, and that was one of the major constraints for using the standard SPE, which was there, or the commercially available SPE to be used in the process industry. What evolved was the Ethernet-APL over here. They adopted the 10 base T1L. They definitely created their own power concept to ensure intrinsic safety. And then there was a trunk and spur configuration. If some of you may remember, Foundation Fieldbus had the similar trunk and spur configuration, and you could bring power into the hazardous area. They definitely used the standard available for the cable, for the safe area, for the higher north side wiring of the Ethernet, but they also adapted the Type A cable from the FF world or even in the Profibus PA world for this application. Some of the standard connectors used and the new standard of 2 wires. Why did we do that? We'll come to that later. So the introduction of 2 wires. Why did we do 2 wires? This was a standard which was developed so that you could run 2 wires, twisted pair cables to your field devices, which is running Ethernet protocol, and it is intrinsically safe. It was based on FISCO Fieldbus standard. It was tested by DECRA, one of the notified bodies under IECX, ATEX, and even for the American markets. It was very quickly adopted by March 21 by the IEC standard as a de facto Part 47, which will be then later on integrated into the -11 and the -25 systems. The basic objective was to fast track this technology into the marketplace with the demands of Industry 4, and then now we talk about Industry 5. It became imperative that all the data available on the field side is is available to management, to process optimization teams who could make and run the production plants more efficiently. Going forward, the two-wire wise standard, what else did we need for the various standards to implement an Ethernet APL? Definitely the the IEEE 802 standard with the 10 base TIL form the basis of the two-wire wise. The cables from 61158 became the standard requirements for part A, for type A cables, and then also the port profiles. We'll come to that port profiles a little later, but there was the requirement that we wanted interoperability. We wanted an application fit for hazardous and non-hazardous. We definitely wanted connection technologies to be consistent to simplify installation, definitely take care of surge protection, and EMI and EMC, the electromagnetic interference. We definitely need to adhere to this two-wire solution, which was evolved for intrinsic safety for the two-wire system. So that was a standard adopted. And then, of course, we have the IEC standard 60790, the 11, and the 25, which is the explosion protection standards for hazardous area. The Dash 14 was also the requirements from an installation perspective. All these standards are adopted under UL 6079. So there are some changes, but the broad brush is that these standards were also adopted into the UL 6079 under the AEX, or what is also called the NEC 505 standards. So more on this a bit later. One of the elements of what you saw earlier when I showed about Ethernet with fiber optics was how could I run fiber optics in the hazardous area? And why is fiber optics or optical radiation an ignition source? I hope you all remember there is a triangle, the famous triangle, or not the Bermuda Triangle, but the famous triangle for explosion protection, or why an explosion occurs. It is the ignition source, it is a fuel or the combustible mixture, and then of course oxygen. And how optical radiation became a source for ignition. There was a research done by PTB in the early 1990s, and they concluded that optical radiation, when absorbed by surfaces or particles which heat up under certain circumstances, can reach a temperature that can ignite a surrounding explosive atmosphere. The good example is using this glass here to ignite the wood, or the laser engraving or cutting machines. When they are cutting or making those cutouts, they heat up the metal around it. So this basically meant that you could not use fiber optics or optical radiation in the hazardous area. The standard was published in 2016, the latest one. The earliest was in 2006, where they defined this protection of equipment and transmission systems using optical radiation. In the US, the NFPA 70 under the aegis of NEC 500 adopted these protections under 3 different classifications, the L, M, and N, and under 505 also under 505.8. They also adapted it as K, L, and M. So what are these 3 protection methods? These are OP, IS. Don't mix it up with intrinsic safety. It's nearly the same or very close. It is OP, inherently safe. Basically, it limits the optical energy running through the cables, which in turn becomes a very limited in ignition energy, and it doesn't create an explosion, whether it is in normal operation or in defined fault operation. OPPR is fiber optics protected. Basically, you are protecting the fiber optic cable or the connection cable in an additional conduit in a pipe, which would then ensure that if there are breakages, the pipe is acting as a protection from the radiation being exposed to the hazardous area. Going forward, it is OPSH, that is interlock. This is an interlock to shut off the fiber optics If the loop detects that there is an open or a short circuit, then from the source or both the sides, when the communication on the receiver and the transmitter, the power or the fiber optics or the optical energy is shut off for a suitable time and allows you to ensure that you repair the problem and then restart the communication. So these were the various fiber optic protection methods or optical radiation protection methods, which evolved as one of the way of transmitting Ethernet over hazardous area. You definitely have cable, and you will see how fiber optic will also be leveraged. So these were the Ethernet based standards that we use. What is the architecture? How is the Ethernet-APL architecture put together? So briefly, and a lot of you will recall foundation field bus. You had the power supplies and you had the device couplers. You have similarly the APL power switch. You have the APL field switch. And then the standard topology, the trunk out, the trunk in and trunk out, so you can loop this up. The spurs coming out to the APL field device, not the foundation field bus field device, but the APL field device. So this is, I would say, a very basic component of the or the basic structure of the Ethernet APL. What more can be done is, and how do they classify with the hazardous area, is that you could have a commercially backbone, a Div2 or Zone 2 valid commercially available Ethernet backbone of field switches, which could be in the Div2 area, could be in the hazardous area connecting to the field devices, which could be sitting in Zone 0, Zone 0, Zone 1, or Div1 environments. The spur length can be 200 meters, and then approximately the distance between or the extension of the network is with the copper cables approximately 200 to 300 meters. You cannot do more with this, and this would be a very good application when the plant is compact, when the layout is compact. You would definitely feed an auxiliary power to these devices because it is not sourcing its power from anywhere else. Going further into a bigger structure, you would have a power switch. The power switch is sourcing the power definitely, just like the field bus power supplies of the foundation field bus architecture. And then it is driving the two-wire intrinsically safe power into the field. How this trunk allows you to run 1,000 meters. And then you have the field devices in zone 2, div 2, zone 1, div 1, and all of them connected through the field switches into the power switches and then to the Ethernet APL connection cards. We call it as, these would not necessarily be an Ethernet APL physical layer. These can be standard Ethernet outer layer. So that simplifies the design, ensures that you're able to use the commercially available Ethernet solutions, and ensuring that you are able to use the Ethernet architecture also in the hazardous areas of the process industry. We talked about port. Why do we need it? Why specify it? Well, a lot of you may remember intrinsic safety. When we talk about intrinsic safety, we talk about the field device, which is the apparatus, which is the intrinsically safe apparatus. And then we talk about the source or the associated apparatus, which is powering the intrinsic field device. And remember, at that time, we used to do what is called operational power. Is there enough power coming out of this power source to be able to load and provide power for the field device to work effectively? 15 volt DC 0.554 watts is the approximate power, one of the power classes available, where you can define on the source side, on the field switch side, and then see that the APL field device also is having the same load. And then you will also ensure entity parameter comparison. Entity parameter loop verification. You would remember in the foundation fieldbus days, we wouldn't have to do much of that because the standards allowed for this entity parameter to be standard across all vendors. And then the field device also complying to those similar standards. So you had the common protection class. So this is what was the port classification. It limits all the variants. It simplifies your design. Deployment becomes easy, and it definitely reduces risk when you're working with multiple vendors, when you are trying to build a design and you are then qualifying your standards and your solution based to certain standards. What are the profiles already available in the release 1? You have the profile for the SPURs, for zone 1, for div 1, for zone 2, div 2. You can do in zone 1, div 1, because the power requirements would be less, you would be only getting 540 milliwatts. But for the zone 2, div 2 devices, where you can run more energy into those hazardous areas, you could do 1.11 watts. And then, of course, you have the non-EXI trunk. The non-EXI trunk is the EXE trunk in the standards if you compare it with ICX or ICX. But under the NEC 500, it will be a non-incentive trunk. You could run this in zone 2, div 2, and you will be able to drive more power into the hazardous area. We expect some more designs to be coming up, more options of the different power classes to be coming up, and expect that maybe in a year down the way, the first ones when the 1.0 versions are coming in, and then you could be even looking for non-EXI devices or trunks for low-cost power switches. A lot of variants are on the roadmap, but we will be, on the Ethernet-APL organization will be evaluating the demand and the adoption as it goes forward. Going back again to the two-wise connection, that's your field device, the power load, the power source, the associated apparatus, the type A cable connected over here, and then of course the standard intrinsic safe two-wire cable going up to the north side. We mentioned that there is a standard IS parameters now. This is your power, your operating characteristics. So you know what is the voltage output from the power source, what is the power requirement of the field device, and you are able to ensure that you won't have any surprises there. Similarly, for the entity parameters, the capacitance, inductance, the leakage circuits, leakage currents are all pre-specified. So you have nothing to worry about connecting a field device, Ethernet-APL field device to the field switch. Remember one thing that you still need to document, because that document recording is required, or recording those entity parameters. Sorry for that mix up on the words. Is required under 6079-25 and also under our NEC 500 OSHA guidelines, because we do need to do change management. We need to record what are the field devices we connect to those switches, and those are then recorded from the perspective of maintaining the history in terms of changes that you would do in the future when you're repairing or replacing. Reduces your engineering design time, reduces your deployment time, but record is definitely a requirement which you would need to do. We talked about cables and connectors, and then we need to be talking about shielding and grounding also. We talked about cables. We talked that we'll be using a fieldbus type A cable. When you're using a fieldbus type A cable, you will be ensuring that these are good enough for IS applications, are good enough, are twisted and are constructed very well for, and have the low LNC characteristics so that they are not a source of hazard when you're transferring power over the cables. Standard terminals, screw or spring clamp, or the M8, M12 connectors. The typical emit enter connectors will be used in the div 2, zone 2, and the screw terminals will be used for the zone 1, div 1 termination. It is intrinsically safe. As you can see, a blue terminal, so there is absolutely no problem that you can unscrew a cable or unplug a connector and still be safe in a hazardous area. And more specifically, the cables specified under the 1158-2, the type cable 4, which is what is classified as type A, allows you to run the cable length to about 1000 meters with a SPUR at around 200 meters. We will not go into all this, but just to share with you that if you are doing other cables, and this could be a challenge when you would want to migrate at a low cost, that you use some of the current cables in your plant and your customer asks you to use them, you could be affecting the maximum distance you can travel. You may be affecting the possibility of number of devices you can connect, and there could be EMI noise, also a challenge over there. So good and bad, you may be able to get an installation, but if it is not effective, it is not noise proof, and you're losing communication packets, it may turn off your customer. So just take the decision, you can say, intelligently, if I can put it that way. The shielding and the grounding concept, again, required. It's a minimum requirements from the Ethernet-APL engineering guide, and that is something which I'll come to later. So you can see the shielding being done, the grounding at the power switch, at the field switch, at the field devices. And of course, these groundings are all equipotential. So what you have in the field and what you have in the control room have to be at the same equipotential. Some of the concepts of what kind of shielding or grounding you can do is through capacitance or direct, depending on trunk and depending on the SPUR that you are using when you're using the field. You can of course read more of that, and when you design it, definitely you refer to the engineering guide. And the engineering guide is available online. The version, if I'm not wrong, this is the 1.1. Covering a lot of the requirements of implementing Ethernet-APL. You have the planning and the design process, the functions, the bonding over there, how you install the networks, what is the acceptance test you need to do to confirm when you hand over the network or the installation to the end user, and possibly some options of migration. Of course, there is a lot of options there for migrations, and that is something we can look at later also. So in conclusion, you now have a standard with Ethernet-APL, which adheres to the standard 10-base TIL. It's just a variant there for hazardous area. Is good enough for all the Ethernet or IP-based protocols. So currently, PROFINET, Ethernet IP, OPC UA, Part IP, and anything else that may come in the future. It has intrinsic safety conforming to -11, -25, and -47, which will allow you to do live work because it is an intrinsic safe circuit, which definitely means a good or a quick uptime in your plants, an easy maintenance process. You don't need to be worried about entity parameter calculations before you put a field device connected to the Ethernet-APL network. You have the Ethernet-APL engineering guide to help you design this. And of course, you will have local standards, which local standards here would comply to NEC 500 or 505. Product markings will be similar here. As for IEC ATEX, it will be class 1, div 1, intrinsic safe, and then 2 wise. The labeling is still being evolved by the NFPA team, so I would wait for that labeling to come up. And definitely it is all approved and suitable for installations in div 1, div 2. I hope I am running on schedule and not far away from the QA session. So We were part of the development organizations. We were part of the foundational field bus and the Profibus PA development team, and we are now part of Ethernet-APL. We have evolved some products, and that is something which I would like to share with you all, how you could use it for your projects. Again, going back, just giving you the visualization, how the products look like. This will be the power switch or the power supply, 4-segment, 8-segment, redundant power supply, depending on the interface connection to the controller Ethernet card, Ethernet APL trunk, and then 300 base TX ports. These would be the TX ports which would be what you call used for any application if you're running directly the field devices to the power supply. The network on the back end is a regular commercially available Ethernet. Then you can power what would you label it in the old days as high power trunk. You could power the field switches, the APL switches, and you could use them to connect to the field devices. These are the zone 1 solutions. These will be with 16 ports. Like if you remember 8 spurs, 12 spurs, field device couplers for the FF segments. Here we are having them as ports because we use Ethernet. So we have a 16 port solution here. And then again, a 16 port for zone 2 div 2. For the zone 2 div 2, for the zone 2 div 2, we have even fiber optics available. And of course, the 100 base TX ports to connect field devices. And then here, again, the field devices for the connections of the over there. Some of the structure that we see as a roadmap for ourselves, we intend to come out with a remote I/O, which will be available on a Ethernet interface, which is already available with an Ethernet interface with PROFINET, with Ethernet IP, and with OPC UA. We would hopefully see an Ethernet APL version also. Once some of the standards are clarified, you could then add a classic IOS, the classic field device, the 4 to 20 milliamps, and still have a backbone with Ethernet APL. And over a period of time or in a brownfield project, you can transition with a field bus power supply and the zone 1 or the div 1, div 2 field switches into the hazardous area. What is the field switch which we already have now is the one for zone 2. Coming up for zone 1 also, and specifically for div 2 for our market. Redundant power supply, 3 of the 100 base, 10 base TX ports with RJ45 in zone 2, intrinsically safe terminals for zone 1. This is the marking label which you can see. Let me see if I can. I'm not able to pull that up. You have an external PT100 and an internal humidity sensor to ensure that when you do a field installations, either in the Alaska region or in the Arizona region, you are able to ensure that the ambient temperature inside the enclosure, which will house this device, is not high and does not damage the electronics. The 16 Ethernet APL ports and probably the Profibus PA, and I'll come to that a little later, or any other mixtures. The 12 EXI ports of half watts or 4 EXI ports of 1.17 watts with 2 wire. Definitely a lot of diagnostics and status LEDs. If you remember, you used to have diagnostics for Profibus PA or FF, where we used to monitor the diagnostics and use either a diagnostic module and then monitor them in the asset manager. You could do diagnostics in the field, and of course it is transmitted over one of the ports available, and then you can transfer the diagnostic data remotely into a control room. Some buttons and displays for diagnostics. Dimensions approximately 6 pounds. It's a robust aluminum enclosure. The zone 1 certification is achieved with EXQ protection method. Screw and spring clamp, as I mentioned earlier, for the Div1 solutions or for the SPUR solutions. And then you can install this on a DIN rail or on a back rail. Here are some images. This is a very small display over here. Some buttons to scroll and enter or go back. LEDs indicating the individual spurs. Are they healthy or are they not healthy? That could be one element to detect them. And you're seeing the product. So did we install it or did we test it? Yes. This is available at the BSF. BSF has been the first one to install or create a test lab back in Germany where they are testing this Ethernet-APL. They have committed to use it for a project in China where they will be implementing, if not all, some of the segments in Ethernet-APL. There was a lot of demonstration done at ACHIMA and other technology fairs in Europe where the Ethernet-APL demo wall was demonstrated, and that's our product over there. So in conclusion to the product that I showed you, what are the features you would see? You do have a real-time clock, you have a web server for local diagnostics and LEDs and displays available. You could have OPC, FDI, that is the PA-DIM, and all those new expected field device drivers available, which will be incorporated. You can do a lot of PROFINET diagnostics if you opt for the PROFINET version. So there will be multiple options over there. Yeah, that's there. You see that the PROFINET version or the Profibus PA version or the standard Ethernet-APL version. Temperature ranges are good, -40 F to 165 F. Power supply requirements, spurs, what is the power that's coming out? Signal level, cable failure analysis. This could be a very important diagnostic features. Unbalanced alarm messages as per any 107. Current consumption, so you know if any field device is misbehaving and drawing more current, you could detect that and would be able to create an alarm. Or if your device is running on a very high ambient temperatures and is damaging the electronics, that would also trigger high power consumption and could be detected. And beyond that, definitely you'll be able to detect the environment around the humidity or whatever. So some of the key features from diagnostic perspective that would be useful when you are implementing Ethernet-APL or Ethernet-based systems. This is just some image screenshots of the product's web server, how we can do diagnostics, how we can even do firmware updates as well. Some diagnostic options where you are able to see signal to noise ratios, the time domain reflections. Again, some screenshots there trying to communicate to the marketplace that we are ready with the product. We have the solution there. The product is not commercially released, but the devices are ready. The test devices or the prototype devices are ready. We would be happy if any of your customers or end users want to build a test bed. There are some talks with some customers in the US who are also willing to put up a test bed. I wouldn't give you the names because of non-disclosure agreements, but there is some expectation that customers in the US will also be putting up test beds to test out this technology. And I mentioned earlier, what about the field device or the Ethernet switch, where we talked about an option where Profinet or Profibus PA. Basically, if I have a Profibus PA device instead of an Ethernet-APL device, I could have the field switch can act as a proxy, convert the Profibus PA into a Profinet protocol, and then your backbone running into your control room will be Profinet based. or it can also be Ethernet IP based, or it can be also HART IP based. So this was just a solution which came out for the standard Profibus PA products available. Similar solutions will be coming up for FF as the technology evolves and for other such field buses. This will be purely based on the demand from the marketplace and the expectations from the market. So I conclude my presentation. This is just an example of the GSDML file, which you can see in your PROFINET configurator. And I'm open for questions. I hope I did well. 10:45. Jose, I think you should have a good number of questions now. The technology is new.
You did a great job managing time, and I also think that you did a great job managing the content, because I don't see any questions yet. So
Okay.
let's provide a few minutes if participants want to provide their questions. Remember, we have a Q&A box. That's where you need to put them. So one of the things that I will say is that this brought a lot of memories back when I was a product manager of a temperature transmitter line. And we had to make sure that our product was compatible for hazardous environments. But while I was really impressed to see how technology has been evolving, and this whole Ethernet-APL is really adapting to, to our current reality of Ethernet everywhere, right? So it's now making it into the challenging hazardous environment space, which has so many other considerations than just what we deal with as a consumer, individual consumer.
Yep.
So looking at my Q&A, I don't see anything. I think it was very, very well presented. Thank you very much, Ravi. Let me now close the event. I will share the last slides that we have from the CSIA side of things. So I want you to all to go and mark your calendar, because June 27th to the 30th, we're going to have our CSIA Executive Conference in person again. After a 2-year hiatus, we're going to have it in downtown Denver, Colorado, a very exciting place. And just the opener of our conference is going to be at Coors Field with a baseball game. We have never done this before. We're very excited about that. So there are many events coming up. Check our website and look at these events that we're having in the coming weeks. Please sign up for them, just as you did for this one. And on behalf of CSIA, I would like to thank you, Ravi, for this informative discussion. I would also like to thank STAHL for sponsoring this event. And of course, thank you all for attending. I'd like to remind you that a recording will be available for viewing within the next couple of days. And be sure to bookmark your CSIA events calendar. One last thing, be sure to check your spam filter for any CSIA emails you might have missed. Even better, whitelist CSIA so you can stay up to date.
Thank you, Jose.
Thank you. If you need to contact us, this is our information. And one more time, thank you, Ravi.
Thank you, Jose, for hosting us. Appreciate this opportunity.
Thank you.
Thank you.